Welcome to today's Explainer. We're jumping right into something that literally sits at the beating heart of modern industry, the control loop. Now, if you've ever stared at a control screen and just felt completely overwhelmed by that massive alphabet soup of acronyms, hey, you are definitely not alone. So, let's decode this core vocabulary of process control loops. We're going to take you from just translating the jargon to expertly diagnosing physical realities right out there in the field.
Picture this. An operator radios you and says, "The loop's fighting me. PV won't track SP no matter what I do to the OP." If that sounds like a totally foreign language to you, troubleshooting any loop is going to be pretty much impossible. But here's the secret. These four acronyms, they're the entire essential vocabulary of process control. They completely map out the path from what's happening right now in your system to what we're actually doing about it.
All right, here is our roadmap for today's Explainer. We're covering the control vocabulary, diving into the four core signals, checking out a thermostat analogy, breaking down the error equation, and wrapping it all up with a field troubleshooting guide.
Okay, Section 1, the control vocabulary. Let's get right into defining these four core signals that exist in literally every single control loop out there. Because honestly, you just cannot control what you can't name.
We're kicking things off with the process variable, or the PV. So the PV is the undeniable, ground truth physical reality of your plant floor at this exact second, right? If you're looking at a tank, the PV is the actual water level. If it's an oven, it's the exact temperature right now. It's always measured by a physical instrument out in the mud, and it is the starting point for every single decision your control system makes.
Next up is the set point, which we call the SP. So if the PV is your current reality, the SP is your goal. It's the exact ideal condition that we're trying to force the process to maintain. Basically, the entire purpose of your control loop is just trying to force your PV reality to perfectly match your SP target. And then we have the output, known as the OP. This right here is where the brain of the operation talks to the body. The OP is the actual mathematical instruction that the controller calculates and then shoots down the wire to make a physical change. So once the controller compares our reality against our target, it generates this output percentage as a command. It's essentially telling the system exactly how hard it needs to work to fix any differences.
Finally, we hit the end of the line, the manipulated variable, or MV. This is the physical muscle of your system. See, while the OP is really just a digital instruction or an electrical signal, the MV is the tangible machinery. It's almost always a control valve, by the way, that physically moves to alter the process. It's that valve stem sliding open or closed, taking the controller's digital instruction and turning it into real-world physical action.
Moving on to Section 2, the thermostat analogy. Let's see how we can map all these abstract industrial concepts directly onto something that is deeply familiar to every single one of us.
Believe it or not, your home thermostat is actually the simplest real PID loop there is. Think about it. The current room temperature that you're feeling right now, that's your PV. That super comfortable 72 degrees you punch into the dial, that's your SP. The electronic signal getting sent down to your basement, that's the OP. And the gas valve physically opening up inside your furnace, that's the MV. It perfectly translates our four industrial terms right into everyday comfort.
Okay, let's test this out. Imagine your thermostat is calling for heat. You know, the little flame icon is lit up on the screen, but your house is still freezing cold. Is that a problem with your PV sensor, or is it an op to MV problem? Think about it. Your target is set, the signal is actively firing, but you are still shivering. Where's the actual failure?
Well, the crucial takeaway here is that this is absolutely an OP to MV fault. Your thermostat's logic, it's perfectly fine. It knows it's cold and it's trying its best to do something about it. The real problem is that the physical downstream chain just isn't delivering on the command. You might have a completely clogged furnace filter blocking the airflow, or maybe the physical gas valve is rusted shut. The brain is working, but the muscle is failing. And guys, this exact same logic applies directly to industrial plants. Which brings us to Section 3, the error equation. Let's look at the simple mathematical engine that actually drives every single automatic controller out there.
This formula is beautifully simple. Error equals PV minus SP. That's it. It just calculates the exact difference between reality and our target in the exact same units as the PV. But don't let its simplicity fool you. This single equation is literally the seed for every automated calculation you'll ever encounter in this field. It's the starting line for all automated problem solving. Let's actually put this equation to work with a real-world example on an offshore separator. Say our target, the SP, is exactly 50% level, but reality, our PV, is reading only 48%. The controller instantly runs our math and finds an error of -2%. Because of that error, it bumps up the OP instruction, commanding the valve to stroke open just a little bit more. Fluid flows in, and the PV climbs right back up to perfectly match the SP, completely neutralizing that error back to 0.
All right, Section 4, Field Troubleshooting Guide. It is time to transition from just reading screens to doing some full-blown field detective work.
But wait, before we start diagnosing anything, we absolutely have to highlight a really dangerous myth. Never, and I mean never, blindly assume the digital OP percentage perfectly matches the actual physical valve position out in the mud. A sticky valve, a miscalibrated positioner, or maybe just reversed action means your screen might proudly say 50%, but the valve is actually only 20% open. You always have to verify.
So, let's test those new detective skills with a classic scenario you're definitely going to see in the field. Your PV is sitting steadily below the SP, meaning there's a persistent gap between reality and your target. But your controller output, the OP, is just skyrocketing, climbing higher and higher towards 100%. What in the world is happening here?
Well, if you guessed a mechanical failure, you hit the nail right on the head. This reveals an equipment fault, not a tuning problem. Think about it. The controller is doing exactly what it's supposed to do. It sees the error and it's shouting louder and louder for the valve to open. But the physical MV simply cannot keep up. The valve might be mechanically stuck, it could be undersized for the flow, or maybe it totally lost its instrument air. The brain is shouting, but the body is paralyzed.
To tackle this, here is the exact chronological rule of thumb that successful commissioning engineers use to isolate a loop fault. Step 1. Check the PV. Is the sensor actually accurately reading reality? Step 2. Verify the SP. Are we even aiming for the correct target? Step 3. Observe the OP. What is the controller commanding? And finally, Step 4. Confirm the MV. Is the physical machinery actually moving? Stick to this exact order, and I promise you'll find the fault every single time.
And that brings us to the end of today's explainer. But before we go, I want to leave you with a final, kind of provocative thought to chew on. If you fundamentally cannot trust the control room's digital OP signals to tell you the actual physical truth of your valve's position, how are you going to change your inspection routine tomorrow? How will you personally bridge that gap between the comforting digital screen and the messy, actual physical reality of the plant? Think about that before you tackle your next control loop. Thanks for hanging out with me today, and keep asking the right questions.